introduce Ken. So for those of you that don't know Ken, you should be very between. Ken is graduated, but he's from UBC. Way back when, it's really 1971. Then he spent 27 years with Utah BHP Minerals as chief geophysicist, where he championed everything airborne. He developed a couple systems out of that. He then went on and started working for himself, founded Condor Consulting, as champion airborne interpretations, Porphyries, women in geoscience, a whole host of other voluntary initiatives. So that is fantastic. Today we're going to learn about porphyry copper deposits and what may be new with the model. Hopefully,
thanks, Russ. Thanks, Russ. That's so. This is actually the 6th time that I've presented this, and you say, "What sort of retread nonsense is that?" But this, to me, is like I'm a graffiti artist, and I've got a big wall, and somebody will come and let me paint whatever I want on that wall. It's there for 6 months and I get bored with it. So I go back to the wall and I start changing things and I start adding things. And this is one of those types of creations where each time that I present it, I work to explain things that I didn't understand when I first presented it or the last time I presented it, and new questions and new ways of phrasing it so that the message, hopefully at some point, gets clearer and clearer. Because the other thing, of course, that we all probably have to admit, and I'll certainly do that, I get bored with a lot of the stuff that comes through the door that I make money on. So like a predator, I like to go out and kill something and bring it in and examine it rather than just eat birdseed all the time. Birdseed might pay the bills, but it's fun to go out and look at data that nobody's really ever looked at properly. And you all probably know there's an enormous amount of geophysical data that hasn't been looked at very well. It hasn't been processed properly. There's nothing wrong with the data, but a lot of companies stall after they get a survey. It goes into some sort of archive. 3 years later, it gets exhumed and somebody looks at this and say, I don't understand this geophysical shit, throws it away. And so we went in 2017, when the industry was getting pretty constrained, went around and started looking at places where there was interesting data. One of them was Chemis. We started that one a little bit earlier. We went to Red Chris, and then we went to Casino, Porphyry up in the Yukon. Both Red Chris and Casino had very decent Quantec surveys, acquired, I think, both in 2009. And basically absolutely nothing had been done with those data sets, because their programs sort of just collapsed after those surveys were done. Chemis, they did 2 surveys, one in 06 and one in 07. The 06 was quite successful in finding a new resource. They came back and finished it in 07. Then they lost the data. They didn't even know they had it. Rob Gordon told me when I was going to get the copy of the 06 stuff, he says, there's a survey from 07. Did you know that? And I said, bugger me. I did not know that. And so, you know, this is the way people treat. There's $500,000 worth of information in there. If it was drilling, it would be sacred. Geophysics, not so much. So, but you have to dig into something a little more than just saying, well, there's extra data out there in the world, and how are you going to do anything with it? But on these journeys, you need companions. And most of these companions, at least in the middle, in the left-hand side, are geologists. Because if you really want to understand what the geophysics is telling you, you have to have people that understand what the geology is. They may not understand the geophysics as well as you think you might, but at least you've got the opportunity to ask them questions as to what this means, why this magnetic feature is here and it's not over here. What does this resistivity feature mean, and the rest of it? And so as a consultant, I don't have these people. Well, I had a few of those guys over in the far right on staff. Scott left us a couple of years ago. Martin is a professor at University of Alberta. Daniel Sattel is a consultant who does a lot of work for us, but all the rest of these guys are basically independent consultants. And some of them, like Dick Tostel, Mark Regobati, they're top of their class. Rob Cairn, Jose Pareo, not known maybe as much up here, but he's certainly a legend in South America as porphyry geologist. He's probably considered one of Dick Silito's heir apparents. So that's a pretty important role. So you got to have people that know stuff better than you. Otherwise, you're kidding yourself. And I had people like that when I worked in BHP, but as a consultant, it's not possible. So these questions didn't appear in the first couple of them, but I felt presentations, but I felt these were important ones. How do we define and then test our geophysical models? And it's not just the geophysical model I'm talking about, it's how the geophysical model relates to the geology. What are we actually going to be telling the person who might actually make the decision to go drill something? How do we couch that in terms of, do we just tell them it's such a susceptibility with certain geometry? Do we tell them certain chargeability, certain density? Or do we try and relate in geological terms to an objective they have? Who's driving the truck, right? It's usually the geologist who's got the drilling budget. So if we don't figure out ways to actually explain our geophysical models, they're probably not going to be very successful in getting uptake. And then how do we build these models from geological information? I won't spend too much more time on that, but there is some work. People like Peter Fulligar have tried over the years to put some things together. It's kind of the mantra. John McGahey at Mira. The problem to me is the rock in the box story. There's not a lot of actual examples that I could take.
Excuse me, could you share the screen? I can see you, but not the presentation.
Wow, thanks, audience. No one said anything for 15 minutes. Yes, we will.
It's your charming smile, everyone.
See this?
Yes, thank you.
Okay, thank you for noticing.
What about the rest of you guys?
Sorry.
Geological models, and I'll be showing a few of those. Typically, it almost is an anathema that the people that define these don't provide any context in the geophysical space. So we're left with like, well, how do we actually figure it out? If they put a model down, how do we design a survey? How do we select a technology? All of the sort of stuff that we're good at, but you say, well, we want to go hunting. And you say, are you looking for deer? You're looking for quail? You're looking for submarines? What's your target? And fortunately, a lot of geologists can't really come up with, other than saying, well, everybody in the district is using Quantec or DS or precision. You say, well, that's not a choice of technique. That's a bias towards a contractor. And yet they don't really have a model in mind that relates to petrophysics, if there is any petrophysics. What do you do when point 4 comes up? You get a conflict between what the geophysics is saying. Let's say the geologist says, we know the structure ends here and there's nothing on the other side of it. Yet the aeromag image shows that structure goes right through. And there's something that looks potentially analogous to the other side. So you're left with a conundrum. Geophysics is saying the geology as defined is likely incorrect. But how then do you move forward with that? There was a good example was during the beginnings of Geoscience BC, 2008, they commissioned a guy called, some of you will know, Colin Barnett, who had still has a very good neural network program to analyze multi-parameter data, be it geophysical, geological, geochemical. He took a chunk of the Quesnel Trough data, geochemical data, reconstructed it by leveling and the rest of it. There was stream sediment, there was lake sediment, there were some soils, brought it all together into a common database, applied his technique, and he defined geological terrains from that data. Then a geologist at MDRU at the time, Bissek, went out and checked it. And he found Colin's predictions were correct, where he said there were intrusives, mafic rocks, and the rest of it. he was much more accurate than the BC Geological Survey map. Workshop in 2014, we had 40 people in the room, and I put Collins' map up on the wall, and I put the BC Geological Survey map up on the wall. And I said, these are what you're facing in the world today. When the BC Geological Survey was asked by Lynn Anglin, who was then head of the Geoscience BC, which map do you choose? The BCGS said, well, we have to choose our map. They just threw out the neural network one that had been field checked. So we have problems, even when we have a very good argument, and often getting people to accept what we see as reality as being reality. This is just the nature of geophysics. So particularly for younger people who are first building their first models and getting excited about finding an ore body or contributing to the wealth of a company or the country, there's barriers of just way people look at information, and you have to figure out ways to get around that. The last one was one which, who are the rabbis? Who are the people that adjudicate models? Who comes in and actually gives us the guidance to be able to choose from a variety of things and say, well, how do you actually arbitrate when you have multiple possibilities? That's one of the things that, yeah, Dennis is right. I mean, do we always go to the lowest common denominator and say, whoever has the loudest voice? Friedland says you can find a Volkswagen down at 3,500 meters or whatever, and you say, okay, Robert has to be right because he's so wealthy. But this is something which I think going forward, we have to think about as a community, who arbitrates models. This is an early one of the Porphyry copper system. It's not the first, but the one in 74 that Gilbert and Wolf put out probably is the closest thing that we could translate into geophysical space, because it's got actual nomenclature in terms of sulfides and alteration that we could envisage what the physical properties might be, even if we didn't have any actual data. It's also the one that was mentioned in a paper by Bill Pelton in '97, which we'll talk about in a minute. So even though we didn't have a lot to go on, people were building synthetic models of porphyries back in the mid-70s. Then it stopped. So we kind of had a wave of good stuff coming out. Largely, it was driven by the work that American mining companies had done, looking for porphyries starting in the late 40s. And when those oil companies shut down those mining companies, some of them like Kennecott in Salt Lake, poured their intellectual property into the University of Utah. Guys like Pelton were there. There were a few others. Riho was there. And they were starting to build exploration models that were very interesting for its time. They actually had a lot of capability and a lot of curiosity, which then appeared to disappear. Jump forward to the current, 2012 is basically current geological context. This is Dick Silito's second version. There was an earlier one about 30 years before this. It's very complex. There's lots of pieces. You can dice and slice it in terms of you're working down here in the bowels of the system, where you're working up here, where there's a porphyry at depth. But nowhere in the document that goes with it is there anything about petrophysics. It's like, this is a static image. It's obviously created through time and space, but it doesn't come to life with the point of view of what sort of density is that? What sort of susceptibility is that? What sort of conductivity is this? It's missing. So it's not an exploration model. It's a descriptive model. Exploration models are different, and we tend to, in geophysics, focus much more on targeting models, whereas geologists tend to like to think about describing the geology. It's not a bad thing, but they're actually the same, they're not going to the same purpose. Back in the 70s, they were very enthusiastic petrophysical collectors. The published date is 66. The work was early 60s, late 50s. I wasn't even in school at that point, I'm in university anyways. So we actually come from a time when a lot of cool stuff and important stuff was being done. And then it kind of just disappeared. And what happened last week? The one maker of petrophysical instruments in Canada shut their doors. That doesn't bode well. Experiments. I'll read it for you. Probably can't see it. So this is an IP survey over San Manuel. This is in the 60s. This is where the original Lowell and Gilbert model came from. Kalamazoo, San Manuel. They were doing depth estimates. These are, feet, chargeability and resistivity of bedrock. They were doing numerical analysis to data in the 60s that are still really not any worse than what we're doing or better with modern computers and all the software that we have. The same questions are being asked, and they had answers to. So that was published in 60. That data is probably from the 50s. This is the first and only paper that I have seen, and others of you have seen. I'd be interested in hearing about it, where the authors invoke the Lowell and Gilbert alteration model as being mappable with Porphyry with an IP system. This wasn't even examples from North America, South America, it was Philippines. That Bill Pelton and Peter Smith put together. Why is there only one paper from 1976 that talks about the linkage between one of the most important mineral deposits we're looking for on Earth now and geophysics? One citation. I will ask how many of you in the room are aware that this is the one paper that has that? Now you do. You're empowered. You become a semi-purple person, like Dennis. Here, an example of an IP survey. I'm pretty sure, given the publication date, this actually comes from the late 40s. So this is the first big system that Newmont built for IP. They did it very, very quickly. And they went and they mapped, call it, there's the pyrite halo, there's the copper zone, lower chargeability, other side of the pyrite. They mapped this at a time when nobody had a clue what the alteration system geologically porphyries looked like. The thing was, Arthur Brandt and his team that put this together never interpreted it as an alteration mapping technique. They just said, oh, that's interesting, and they moved on. So they had data, but it was like having access to the Hubble telescope and not knowing that the Earth and the sun were the limits of your universe. They did not have the understanding necessary to extend it. And geologists clearly weren't looking at this stuff from the point of view of an alteration technique, but they probably did find a few systems using this sort of approach. But it's interesting how this, fast forward to 1974. This is an example from central BC. Again, pyrite halo, outside prolific alteration, central potassic core. That's where the copper is. So the model's robust. It's been around for a long time, but very few people actually are aware that it exists. Here's some examples of things that are into the space of less traditional. So we have slides before this are the things that IP got to be known for eventually. But now we are entering into another phase, which we found that there's things going on in a number of porphyry systems, not necessarily all of them, but are totally missing, really, from Dick Silito's sketch, his model. And because there's a lack of any petrophysical definition in his model, they don't really know how to change the exploration parameters to go look for these things, because it's like, well, we use IP, we use MAG. We've always done that, right? It's not wrong, but you're going to miss things. And these 6 deposits show that. Located casino up here in the Yukon. This is the NAC deposit. was just got added. It's new into the pile. Bingham, Resolution, Collahuasi, and then Reykjavik over in Pakistan. Wasn't going to put Pakistan, didn't need to. It's there. And where does this, and this largely comes into the conductivity space issue. We're looking at bulk properties, veins and massive sulfides, and supergene. And I'll jump forward to a question that I felt I had to ask. How many of you have touched or encountered a supergene blanket that's been conductive? Hands up. One hand. Would you expect it? Do you know that that's parameter? Supergene blankets. 2021, Don Emerson, who was the petrophysical guru in Australia for years and years, published a paper in Preview, shows the conductivity of chalcocite, which is the primary constituent of supergene, is conductive. I have not seen any geological publication that recognizes that fact. But not every supergene blanket is conductive. The one at Casino isn't. The one at Silverbell isn't. Some of them are and some of them aren't. I was having a conversation with Christian Dupuy today about the possibilities of getting one of his students to look at the petrophysics, supergene systems, and find out why some are conductive and why some aren't. Because that's something we should be armed with. So supergene got added in to the discussion because it's a very, you know why it's important? Because supergene is much easier to mine. It doesn't have the metallurgical headaches that primary sulfide ores typically have. It doesn't have the physical hardness that requires more explosives to break it up and put it through the system. And the grades typically are 2 to 3 times higher than the hypogene grades. So supergene has been economically, in the last 50 years, the most important mineral coming out of most porphyry systems. So we should be paying attention to it. Bulk properties. This is work that Kennecott did back in the 70s. This was actually done on not macro scale surveys inside porphyry copper deposits, open pits. So resistivity values here, and then the percentage sulfides, you can see there's a relationship. The sulfides nudge up towards 10 to 20%. And there's also this transition between disseminated with stars or triangles, circles, and then the little glowy bits, continuous veins. So the continuous veins tend to be the most conductive. And that makes for an interesting problem when you're doing IP surveys, because we saw this when people were looking for VMS with IP. You often had great difficulty in mapping them out because the strong conductivity and the DC resistivity tended to smear any sort of chargeability response. So you saw something, but it was difficult to interpret. And that's why probably EM became the tool of choice for most things like VMS. Porphyries, it's a transition thing, which people haven't really grasped, that you can actually have significant conductivity. Supergene being one source, veins can be another. And so we go on. One geologist who did try to get his head around the story was Jeremy Richards. I first met him when he was at the University of Edmonton. Then he moved to Laurentian and he passed about 3 years ago. But he actually put this cartoon together. These are erosional surfaces. So with bulk properties, rock type alteration, sulfides in resistivity here. So basically looking at the sulfide concentrations as presented by the resistivity parameter, magnetics, and then chargeability on the far right. And this is about the only effort that you won't see anything like this in work that people like Silito and others have done. It took being in a geophysical paper for Richards to actually put this together. How many of you have seen this before? Okay, it's good. Advancing. Here is a expectation of what the bulk properties would be in this case. Jeremy didn't get into the granularity that the Kennecott people did with veins. He knew they were present, so he was truly trying to give a bulk response. Examples. This is the an outline of the casino deposit in magenta. Around through here, this is the block of lines of the context survey. It's a little constrained. And one of the things we probably don't see, there probably is a pyrite halo development around here, but the context survey didn't go far enough out. So we really only got information about the central core of the property. Very large tonnage, modest grade, remote, but it's one of these resources of the future. We processed up the data. This stuff in kind of blue. This is the copper. This is all primary supergene. And you can see this sort of odd behavior. You've got something along the surface here. That's the outline of the deposit. This is actually the supergene going down a fault. So with the oxidizing fluids flowing vertically, the copper dropped out along this fault surface. This was the thing that caught my attention. The gap is a geophysically anomalous feature. We had no clue what it was, down about 600, 700 meters. We presented it to the owners in 2017. They put it into every one of their corporate presentations, but nobody stopped to think, well, what was it? I couldn't even stop to think what was it. It was like my processing guy said, that's one of the most robust features I've seen in any MT data set. It's not going away anytime soon. So that was good enough. So we left it there. Last summer they drilled it. Kilometer deep hole. Get to those. Okay, we've got a slide on it. So this is actually from their website, how they described it. It wasn't actually, this was not the case. It wasn't in the contact report. They didn't recognize it. They were flummoxed by one of the major heterogeneity in the response in the near surface, because the one of the interesting critical things here was this part of the Yukon was never glaciated. So all of the original oxide and supergene and hypogene preserved. So it almost, other than uplift and some erosion, this was like how it formed and then started to weather. In fact, this deposit was found by discovery of an exotic copper deposit, like are normally only thought to be found in Chile and Peru. The geochemists actually got onto one of these because it was the copper was dissolving and coming out down the topography and then reforming over here. This, on the other hand, nobody quite knew. This is the 1 kilometer deep hole. They went about 200 meters into the body. And trying to get it. So there's the drill hole piercing the target at this point, and that's semi-transparent inside. So what they got were 3 down in here, 3 intersections, 3 meters, 5 grams gold, 1.7 gold, 3 gold, silver, copper, copper, copper. In this. In for a penny, in for a pound. Ladies and gentlemen, what does the client do? I put it in a paragraph, but what would you do? Kilometer deep. Suggestions. First 2. Another hole. How about downhole geophysics? If it's really conductive, possibly. What's that?
Find somebody who wants to buy it.
Well, Rio Tinto's invested and Mitsubishi just came in. So they have people that are interested. See where it goes. So we're left with, this sits beside a major structure. And the possibility is that there was a charge of sulfides, I think, a charge of sulfides that built up. And then there was a fracture, a brecciation event. And there was a sudden decrease in constraining pressure, and it just shot out and it precipitated. There's actually people like Cam McQuaig and John Horonsky, both Australians, have proposed these sort of what they call self-organizing systems. This is where geophysical input could really help the geologists, because they don't really think about these things very much in terms of dynamic processes inside systems that are different and odd. The NAC, we did some work on it. It's a porphyry in central BC. It's found by Miranda back in the 60s. It was picked up by a junior in the 2000s. They did some IP. They ended up doing a ZTEM survey. Then they walked away. They're very little drilling, but they drilled fairly shallow holes. There's two recognized systems. One's the Dorothy, and there's the NAC. The Dorothy now, from a property perspective, AMARC has carved out this part, and a junior called American Eagle picked up the NAC. And they there's the mag, very nice mag feature associated, that intrusive. There's the TPR from the ZTEM survey. That's kind of the feature we think is interesting. That outline, of course, comes from some sort of geological mapping, but we seem to have a reasonably close correlation between the two. Here's a zoom in. What American Eagle did was, rather than drill 200-300 meter holes, they went down 5-6. What did they find? That. Massive sulfides down in the system. So up here, you know, the previous owners drill down to this depth, squat. Doesn't laterally go all the way. There's something up in here that got them excited, but then it continues. So the ZTEM actually helped give focus at depth that was not obvious to the previous operators. And of course, the IP survey was really only giving information down to about here, the way it was run. Now, a modern 3D array system, different story. That wasn't available when they ran this in. So there's a story unfolding there, and it's pretty cool. Quebrada Blanca is a very interesting area. Coyawasi is the group name. There's Quebrada Blanca, which is controlled by Tech. It's one of the things that whoever might buy them in copper would be very interested in getting, because they just spent a pile of money upgrading it. Rosario, which is owned by Glencore and Anglo, and Uhina. These are all largely found by Chevron back in the 90s. And this site was the location of, here's the names there, all their characteristics. We know from publication, Quebrada Blanca is a very significant chargeability high. I haven't seen the data, but indications are the supergene there is quite significant. So I'm putting it down as a low resistivity due to the supergene. Rosario, chargeability high, resistivity low. Uhina is the same, but the reasons almost opposite why it's that characteristic. Uhina is dominated by a supergene blanket. Rosario is dominated by massive sulfide veins, totally different piece of geology. Both have strong IP responses because of the disseminated mineralization, but the conductivity is coming from quite different geological sources. There's the IP, knocks your socks off. There's Uhina there. There's another little spud over there. The main zone that was open pitted, Rosario is up in there, but the whole system extends considerably further out to the southwest. Resistivity, very conductive center point there. Here, there's a strong center point up in here, but it extends considerably to the south and the southwest. What's the geology? Veins and massive sulfides. Okay. Back to the picture, continuous veins. That is what's present at Rosario. This is work guy Mike Wilt. You would have met him in Berkeley. This was part of his PhD thesis. The rodent never presented that at a geophysics meeting. It's in his thesis, and it's really interesting. But at least he told me where it was. So he didn't actually do this work. This was done by Krohn in the 1980s. And the porphyry system sits here. These veins cut through it, and they are very, very conductive. They're running 15% chalcopyrite. The company built the mine on the veins and then mined the porphyry as gravy afterwards. Lots of places have veins, and the geologists won't tell us that they may be very conductive. And we go in and we run an IP survey, and we get a really messy resistivity product, and the IP is crap because it's dominated by low resistivities. You can't really get proper data. But if you went in and did a EM survey, you'd actually find something that would be drillable. This is the results from surveying those veins at Rosario. This is a model, and I get a little worked up when I show this. So where did I find this model? Did Joel Jansen give it to me? No. Did anybody at Xstrata give it to me? No. There was a financial tour presentation, 2006. Glencore was presenting to a bunch of pencil necks over in London. And they had 4 geophysical images that have never appeared in any geoscience publication showing the conductivity around Rosario. So you have the porphyry system here. It was Tony Watts and Tim Walmsley went in 04 and 05 and did a round EM system survey. These are grades. This annulus, the next picture will show it a little bit better. Here's the porphyry. These veins are producing this enormously conductive, enormously large, enormously rich zone. And EM, Tony says, I fought like hell to try and get a borehole survey, and they told me piss off and go back to Canada. But they are mining it. So real live, very strong conductors sleeping underneath the pampas. Bingham. These are, that one's a pretty clear one because you can get that off out of econ geology. Here we start to get some images. So Bingham's the big guy in Utah. This is a MT survey that was organized there probably in the late 2000s, 2002 to 2010, something like that. And they actually got data inside the mine too, which was very amazing. So we see there's the pit, and there's this big conductor here. And you say, well, that's probably just mine equipment, right? Big trucks, big shovels. That's where it sits. Another gaff. There's the surface. There's the pit outline there, the green. There's the neck of the stalk going down. There's this feature down at 2 kilometers. So what in jumping Jehoshaphat is that? I asked Donald Higgs. I said, Donald, what have you got there? He says, oh, it could be conductive water. Could be clay. You weasel. It's freaking mineralization. But he couldn't say that. Rio Tinto has this, it's prohibited. That description there, I'll skip by it. It's in the PowerPoint. Massive sulfides. They're starting to mine right here. Their curiosity in this feature, these are 2 kilometer deep holes. And I said to Donald, I said, you drilled 3 2 kilometer deep holes on saline water? Seriously, man. So sometimes people are a little silly. And I apologize for the skewed look because Donald gave this talk in 2014 in Elko. And not by me, but somebody else surreptitiously recorded it. But the camera happened to be sitting at kind of an off angle. So these all look a little, nobody's been drinking. It's just the way it goes. Resolution. This is a fun one because it has at least the legend that when this MT image, data acquired by Quantec for Rio Tinto, was shown at Exploration 07, The gentleman who showed it lost his job 6 months later. Rio Tinto did not like having their secrets revealed. There's the unconstrained. There's a constrained model. There actually is here a saline unit sitting over top of it, but this feature is fairly clear. This is the sulfide concentration, 7 to 14%. There's the ore zone there, brushing up against it, part of it. There's another sketch of the geology, and the ore zone sits in here. So MT first highlighted this very massive like shield over top of the deposit, very conductive. This is the modeled Z-Chem results. There's the ore body here. So we're getting these blobs. It's a very challenging environment for natural fields because of big power lines. Very, very noisy. We thought we got something out of it that was interesting. Supergene, wrap it up here. Here's a shot from Don Emerson's work. He looked at density, increasing density and increasing conductivity. Graph in the yellow is the chalcocite. It's not, the problem with Don's stuff is it's not representative of a bulk property, it's point information. So what you really need is something like scale, like what does a piece of chalcocite the size of this table look like? Not what does a piece look like conductivity wise. And that would be something that if we can get a program going, would be the sort of question we'd ask the researchers, is that when you figure out the scale of why these. Sillitoe has a 42-page poem about supergene, and nowhere does he see anything about how to find the next one, or that these things are conductive. He has no clue. So we can't really turn to our geological brethren because they haven't asked the question. They haven't looked at it. We have to do it. It's going to be done. This work was done by a contact, a guy called Randall Nickson. Some of you might know him. He was being frustrated by presence of what we call caliche. This is an evaporite, covers a lot of the hyper dry areas of Chile, parts of Peru, and it's hell to get through for electrodes. So he brought down a geonic system in 92 with support from Chevron. And this is the geology, this is the location of the blanket. This is what he got for the TEM system. So he was able to map that supergene zone very effectively. And one for just good old time's sake, this was a BHP discovery in Pakistan. Barrett currently has it, and Bristow figures he can develop it. Good luck to Mr. Bristow, Barrett. Chalcocite zone. Looks like that. Very uniform across here, so it's nicely developed. Oh, that's actually that was the conductivity. I should have said that. So that section line goes through something like that. So yeah, the thing is we couldn't get an airplane into, we wanted to fly it, but the authorities in Pakistan, Afghanistan is like a stone's throw away. And it's never a place you want to go flying around unless you're heavily armed. This I throw up as a possibility for some of the reasons why these large quantities of sulfides get distributed as opposed to disseminations. Disseminations is sort of like, to me, a teapot bubbling away. It's a much more gentle process. But when you start to get big sulfide systems occupying veins or sitting off to the side of casino or above resolution, something has come out very, very quickly. Very quickly. So there's a dynamic going on in here. Geophysics is providing insights to. We have to get geologists thinking about this from the formation of systems. Because if you can find these massive sulfide systems, you have tapped into something which often has very significant economic implications. And they could be sitting underneath or beside. And the geologists, unless they drill, they won't have a clue. So major target, Porphyry copper since the end of the war. Basic signatures were understood early on but largely around the concept of disseminated mineralization. Then eventually they picked up on the alteration, they added that to the story. So we could explain reasons why we get the zonations and things like that, which is all good. But there's another, to me, another layer in the systems that we have not addressed. People have not come out and said, we also have this, and we should look at this because if we can, we've got better ways of finding them, and we also can impact the economics. So current geological models are not adequately capturing important petrophysical attributes. I think that to me is a slam dunk. So a really, really good resource on porphyry coppers has come out of largely the deposits here in British Columbia. This book in 76, which is out of print. That book in 95 may not be out of print, but it's really hard to get. That one was just published. I have scans, both of those. If you send me a receipt that you bought that one, I will send you a PDF of the other two. So you've got the complete set. And you will have the best resource on geology, porphyry coppers that I've ever seen. So that's it.
Any questions?
What percentage of porphyry deposits would have this vein system? In other words, how successful is EM?
One that comes up to that question, one that comes up in some of the geological stories, like the guy who wrote up the Rosario, he put 3 or 4 other systems that had similar veins. There's not a hell of a lot of information on them, but he said that they had them. And so you can surmise that potentially they would also be, they might be conductive. One that seems to get a thumbs up is Butte. Butte had there's very significant D veins. The thing was they were mined back in the 20s and 30s before even Anaconda was really doing much geophysics. So other than the photographs or whatever of the mineralization, we simply don't know. I talked to the guys at Imperial. They had a deposit which was on the border with Washington State that had a very significant vein system. And the speculation was that it could be conductive, but it was in a very environmentally very sensitive area. And they actually, bless their pointed heads, they turned the property over to the government as a park. So no geophysical surveys will be done there. I've thought about that from a sort of a statistic point of view. And I would say maybe 10 to 15% might have something like this. It could. I haven't gone through the literature looking for descriptions, but yeah. Okay. And do you know of other people that have actually gone and done surveys explicitly to find supergene blankets?
No, I don't know.
Okay.
But
the veins. Yeah.
we found out.
There you go. Okay. I think I've listened to that talk.
was the EM.
Okay, right.
So it's high enough to encourage you to suggest to clients that they should be doing EM. It's a fairly routine expression.
Well,
In addition to.
Yeah. where it sort of, Dennis, it sort of twigged. We were doing a big project for one of the native corps in Alaska. And huge block of ground with very, very little work. And there were like 14 porphyry targets within that property. But none of them had more than like $1 million worth of work. And they were never going to see much more than that because it was too damn remote. They had no way to upgrade them. I made actually a proposal at a couple of roundups. I said, the one guy sitting beside me who had one of these systems, last guy said, go run, half dozen lines of MT. You can either thumbs up or thumbs down. If you have a system like this, you potentially could, put an underground mine in and, maybe never deal with the porphyry, depending on what the economics were in the remote area. But I said, if you had 14 systems and you did 5 or 6 lines of MT, you'd have like half a summer's drill program to basically go in and say, what are the top three that I maybe should be spending some time on? Just to advance the project. So, yeah, given some thought to what the economic implications would be. I've chided the people at Geoscience BC to go get some freaking MT data over the Australians are covering their whole country, and we still don't have good passive field electromagnetic information, because that probably need that to get the depth. That would be
A little bit tougher place to work.
yeah, oh yeah, I mean, there's reasons for sure. But you know, we should have calibration, should be able to go out. I mean, Chemist has got some interesting responses that show up in the Z10 survey, and there's MT from the two Titan surveys. So that's another one that's showing something, and I think there it could well be the supergene. But we're pretty sure that the southern deposit, which was mined, Chemist South, probably was. It's actually a faulted slab. It's been decapitated. It's sort of just sitting there. So there's no likelihood of anything great depth there.
Some of those cases, wouldn't you recommend Z10 first?
Yeah, I mean, yeah, the thing is how big it you usually probably put a box around a, you know, porphyry system that's going to be 3 to 4 by 5 kilometers, and that's not a huge airborne survey. It's yeah, and then as Dennis said, the logistics of whether you're going to be scrambling around them, you know, along with the mountain goats, or if you want to fly the thing. We've picked up as many Z10 surveys as we could. The supergene is interesting because at Casino, it's well developed. It's well developed at a deposit called Silverbell in Arizona. It's actually being mined for supergene, but they're not conductive. They're dead resistors. Dead resistors. And that to me is the conundrum of it. You just don't have the understanding why the same mineral in two places is so different in its electrical properties. Well, I mean, Emerson did it on the mineral. It comes out as sort of a smoky. It very seldom does it form crystals because it's a precipitate, right? So it doesn't have the high temperature component that maybe good crystals might come from. Blah blah blah. Don't really know. It's one thing that the U.S. companies did not seem to look at. You can't find, whether it's Arthur Brandt or the guys at Kennecott or various other U.S. mining companies, porphyry copper companies, they don't discuss the supergene story. I don't know why. Maybe it's top secret. Didn't want to talk about it. So, yeah. But how can we've been looking for something for 70 years? We've still got fundamental questions that we haven't answered. I mean, it's both exciting and like, oh, we better get to it soon. Somebody better get to it. I'm just selling the book. No, I'm not selling the book. I'm giving the book. And they actually, that one, the 2021, has even more. The amount of geophysics sort of goes up like this. So you're getting good value with those things. They're commenting like that.
You have to get that through CIM?
Yeah. That's the easy one in 2020. And it's not cheap, but it's good value. Compared with having to attend a conference.
I send you a copy of the receipt.
I'll send the other two. I'll send you a link to the other two. One guy in Australia made the offer and got it. Yep. Yeah. So does anybody on the?
Yeah, we have 24 people online. If anyone has a question, just unmute yourself. You can also show your face if you want to or not.
I'd be curious from your perspective then on, among the sites you've shown, kind of thinking about a computational research group, thinking about role of inversions, if there's places that you think would be really worthwhile to delve back into data sets that would be, that have some real questions that, we've spent some serious time seeing what we can tease out with the latest and greatest, what would be worthwhile and what sorts of questions do you think our group could perhaps bring to them?
Well, I think you would would be most likely be able to generate something with the greatest likelihood of making advances if you can be presented with effective petrophysical information. Because I think we're still lacking the work process, workflows, to know how to use that information. And I'm sure it's not a unique experience, but the client will tell us, oh, we've got petrophysical data. And you find out one geologist 5 years ago logged sus on 5 holes. And it's like, what do you do with this? You need extensive information across these deposits to constrain me, I think, but it's not really, we don't have a perfect test site where you can say, right, here we're going to use all of the information we have. Here we're going to use 50% of it. Here we're going to use 25%. How much information do we actually need to make a better model, to make a model that fits geology better? The thing is, we have to be prepared. We're going to be raising questions that geologists have not had to answer before. And so there's going to have to be some framework for the dialogue and arbitration on the models. We're going to need some rabbis. We're going to need some people that are actually have skin in the game, but they're not backing one horse, right? They're trying to we need to get better at it.
Do you know of any sites that have good petrophysics at this point, or is that still?
Probably the best ones are it's the iron ore. They spend a huge amount of money on logging and stuff like that because it's all grade control. They need to figure out what the grade is so they can stockpile it. I mean, I visited the Utah or BHP mines. I thought it was boring as hell. You drive up and it's all orange and it's like, oh man, what's a geology? Iron ore, come on. Thing is, they had to deliver 27 different types of ore to their various clients, different sizes, different grades, because many of these smelters had blast furnaces had different criteria, particularly the Chinese. There was a whole bunch of issues related to that, and I said, wow, that's really. And then the other part was what I really liked was the awesome trains that they used to call this stuff. But yeah, I think the iron ore people have they put a lot of time and money into using sophisticated petrophysical. I heard at one point that the De Beers people did quite an extensive amount of. I think they used Quantec. This would be about 10, 15 years ago. They kind of wanted to do an inventory of all their pipes, economic pipes. Whether they had petrophysical data to complement it, I don't really know. But yeah, maybe we should start here in BC, just get Geoscience BC to, tamp down the geothermal and get some more.
Well, the Australians have done a really good job on those volumes. They process in different areas, and they include the geophysical responses.
Yeah, they're compilations. They don't have a lot of inversion though. Fine.
No, well, at the time,
Most of the compilations they didn't have that. But I mean, I showed some examples from the 70s. People were doing, I mean, Bill Pelton, with help from it was Kennecott, we had a 2D IP inversion program. It was a lookup table. And it worked. I used it for about 5 years, and it was fast because it was just there was no inversion required, and it only worked for 2D sources, but it gave some pretty reasonable results that we could work off of. So, but then that all kind of disappeared. Bill apparently left, and he pissed off Stan Ward because he took the source code for his program with him. I think that was under direction from Phil Halloff. Bring everything. This project I'm looking at on the history of EM in the 50s, that turns out somebody said, well, both copies of Stan Ward's thesis were taken out of the University of Toronto library. Both copies. How popular are people's PhD theses now, right? Is there really, well, they're all digital, so it's a different story. Yeah. But they're all quiet. They must be having the second scotch, good on them.
Answered everything.
Ken and Lindsay.
There we go. One more. Sounds good. Go for it.
Yeah. Yeah, it's Christian. Hi, how are you? So
Christian.
So to answer the question, we've been acquiring more and more physical properties. So there's a few things regarding IP and resistivity in basically gold sites right now that are looking kind of interesting. We can see like alterations. So it might be useful. We're looking at it sort of like at the small scale, but looking at upscaling what we're seeing in boreholes might be useful.
Sounds great. Lindsay's gonna call you back.
Yes. Okay, Christian.
Thank you very much. Okay, well, thanks again. Let's just applaud Ken one more time to thank him for coming.
Thank you for coming.
The YouTube's gonna be online soon.
Good. Send up, you do put the link out on your website?
Yeah.
Yeah, it goes
Yeah.
on to it, and I usually plug it in. Awesome.